Let's study chapter number 12, study of sound. Now children, when you are at school, when you are at home, sometimes you hear certain disturbances, and these disturbances, when it comes to your ears, you feel something. Now you say, what sort of sound this is? It is troubling you. What sort of sound this is? Now we will study here what do we mean by sound. Sound is a form of energy which creates a sensation to our ears. How do we hear it? We hear it through our ears. Whenever there is some sensation created due to some energy, it comes to our ears and then we can hear, and then we say what type of sound this is. Now this energy is in the form of waves. When it comes and hits our ears, it is in the form of waves. Now for these waves to travel from the place it was making noise to our ears, it requires a medium. So a medium is necessary for the propagation of sound waves. Now sound waves gives rise to compressions and rarefactions. It gives rise to a chain of compressions, rarefactions, compressions, rarefaction. Now what are these compressions and rarefactions? Now compression is a place of higher density where you get maximum sound, and rarefaction is a place where you get less sound. The particles of the medium oscillate about their central or mean position in a direction parallel to the propagation of the wave. When this happens, such a wave is called as a longitudinal wave. Now let's take an example. If there's a still water, you take a stone and you throw the stone in the still water. What happens to the still water? What do we observe? Our observation is that the particles of water oscillate up and down. These oscillations are perpendicular to the direction of the propagation of the wave. Now such waves are called as transverse waves. As you see, we have got three figures over here. The first figure shows us the change in density, the second figure shows us the change in pressure, and the third figure shows us the changes in the density or pressure. Now at any moment during the propagation of a sound wave, now when a sound wave propagates, at any moment you may find bands of alternate compressions and rarefactions. Now what are these compressions and rarefactions? We have already done. Compressions is a band of greater density and rarefaction is a band of lesser density. Figure A shows us the changes in the density. As I already said, figure B shows me the changes in the pressure, and figure C is a graphical representation of either the changes in density or pressure. Now the wavelength of a sound wave is indicated by a Greek word called as lambda, and it is given by this symbol, while the frequency is indicated by mu, and it is given like this. The amplitude, which is the maximum, it's a maximum value of pressure or density. Amplitude, which is the maximum value of pressure or density, is indicated by A, amplitude. The time taken for one oscillation of pressure or density, maybe pressure or maybe density of a point in that particular medium, is called as the time period, and it is indicated. Now this time period is indicated by T. The value of frequency determines the pitch The value of frequency, what it determines pitch. Now what is this pitch? It may be high, it may be low. Of the sound, it determines the pitch of the sound, while the amplitude determines the strength or loudness. Study velocity of sound. Now you and your friend both will perform an activity. Now you have seen an iron pipe in your schools, near your houses. Now tell your friend to stand at one end of the pipe around 20 to 25 meters, and you stand at the other end and put your ear to the pipe and tell your friend to tap on the pipe with a stone. Now what do you notice from this? Yes, we notice two types of sound. One sound which comes through the air and one sound which comes through the pipe. Which sound will you hear first? The sound which comes through the air or the sound which comes through the pipe? Yes, the sound which comes through the pipe will be much faster as compared to the sound which comes through the air. From this, what do we find? We find that the distance covered by a point on the wave, on the wave in unit time is the velocity of the sound wave. I repeat again, the distance covered by a point on the wave in unit time is the velocity of the sound wave. So velocity is given by velocity is equal to distance upon time. This is the formula for velocity. Velocity is equal to distance upon time. Any point on the sound wave covers a distance equal to the wavelength. Now the wavelength is given by lambda in time t. That is the time period. In time t, which is the time period. Thus the velocity of sound will be given by velocity is equal to wavelength upon time period. Wavelength upon time period, which is equal to, what is the wavelength? Velocity v is equal to wavelength lambda upon time period t. Now look here, v is equal to lambda upon t. Now v is equal to, now 1 upon t is equal to mu. So we will write mu lambda. Why? Because 1 upon t is equal to mu. Okay? Thus from this what we find that velocity of sound is equal. What is velocity of sound is equal to? Equal to wavelength multiplied by frequency. Wavelength multiplied by frequency. In any medium at a fixed physical conditions, the velocity of sound of different frequencies is nearly the same. Now if you take, the velocity in solids is highest, whereas in gases it is the least. Now it increases with the increase in the temperature of the medium. Now let us see, the velocity of sound depends on certain factors. Now what are these factors? First, velocity of sound in a gaseous medium. The velocity of sound in a gaseous medium depends on certain physical conditions. Now what are these physical conditions? The temperature, the density of the gas and its molecular weight. Next, temperature. The velocity of sound is directly proportional to the square root of the temperature of the medium. That means velocity directly proportional to the square root of the temperature. Now what does it mean? This means that increasing the temperature 4 times doubles the velocity. Density. The velocity of sound is inversely proportional to the square root of the density. Now velocity is inversely proportional to the square root of the density. Now this means increasing the density 4 times makes the velocity to half its value. Molecular weight. The velocity of sound is inversely proportional to the square root of the molecular weight of the gas. We inversely proportional to the square root of its molecular weight. Now what does it means? The increasing the molecular weight 4 times reduces the velocity to half its value.